So there's a little bit of discussion in the piazza about C++. I actually, for the last 3-4 years, have been bugging NERSC to upgrade their compiler, default compiler, to whatever is the most modern one, with not much success. So what does that mean? If you go and say, capital CC, -v, you'll see a couple of information about what is this, CC is this wrapper around compilers, right? What kind of a compiler is used underneath? And you'll see that it's, by default, some Intel 11, 13, whatnot. And then it will say GCC compatibility 4.0.3 or 4.2 point something. Some number will come out which is significantly lower than the latest GCC. That's why sometimes you need to put STD, C++ 14, so things like that. And so, yeah, you can do that. Just put the flag. Once you swap to GCC environment, the chances are it will automatically either load the newer version, or if it doesn't, you can say module load GCC, and it will bring up the latest compatibility mode, which usually is 6, so you don't need to do that flag. But there's multiple ways to get around this, so that's basically the bottom line. But it's there. It's not just enabled by default. That's the main issue. Okay, welcome back. So the lectures, just a reminder, last time we talked about distributed memory programming. We talked about network topologies. We talked about analyzing performance of distributed memory parallel algorithms. We talked about the alpha-beta model and why it might be coming short sometimes when all the processes within a node, more than one, is communicating, but why you should still probably be sticking to it because it's actually is understandable and makes algorithms comparable. I don't know whose book is this. And then we did hello world. We calculated pi. We're using MPI. We talked a little bit about the history of MPI. And here we are. Now, what I'm going to do today is I'm going to go over some of the collective operations, which for personal reasons, I believe are the most convenient aspects of MPI. And then we'll even see how one of them is implemented, and we'll give hints about what others are like in practice, so you get a sense of what's the performance model there when you call some collective operation. Then we'll talk about the non-blocking versions of those. The pi example you've seen was blocking, meaning that the sender who was sending had to wait until that message is completely emptied its buffers, and then the receiver was waiting until all of his buffer is full with the message, the incoming message. So those are the blocking, and we'll see non-blocking versions of them, and in particular non-blocking collectives as well. And then we'll go into how to deal with MPI plus some sort of multi-threading. So this is becoming more and more common, especially now that you have access to Cori with lots of cores. In fact, if we assigned you KNLs, you would have even, I think, 68 cores within a single die. What that usually means that if you try to do one MPI per core, then you lose a lot of performance just for that overhead and the network interface card overhead. So you will end up having to do some sort of multi-threading within the node and across the node some MPI. And there are some pitfalls there that you might want to know about MPI, how that interacts with multi-threading, and we'll talk a little about those. And that's probably going to be the end of it. So what's collective data movement? A couple of simple ones. Broadcast. Some processor owns the data, and it wants to share it with everyone else. Pretty simple model. The syntax is very nice, too. You just basically say broadcast, give the address, and everyone calls the same function. The only difference is you say who the root is, basically who's owning the valid data and who's owning the either uninitialized or to be overridden data. Scatter and gather are duals of each other. In the scatter case, one processor has data that's usually on the order of the number of processes, some multiple of the number of processes, and it wants to distribute it to everyone. Like the first piece goes to, it stays with itself, the second piece goes to the second processor, and so on. And the gather is the inverse of it. You basically have data distributed across processors, and you want to gather it into a root, so-called. And in this example, the root is P0, but you can specify anyone. So one important aspect is these functions should be called by all the processes within the communicator you're calling. If one of them doesn't call, the function will block indefinitely. That's usually the beginner's deadlock case in collectives. If you have a code that uses a lot of if-else statement or lots of recursions, you might actually get deadlocks because some process will not reach the collective, and then it will get stuck somewhere else, and everyone else will wait in the collective. So that's usually one of the first mistakes people do. I've done this. It's okay, I mean. But know that that might be the cause of your issues if you ever experience this. And I told you about what the root argument is and how that goes. But there are versions of collectives where there's no root. And these are all gather. Like this looks awfully like gather. You remember what was happening in gather. If the top call was a gather, A, B, C, D would be gathered at the root. Instead, it's gathered at everyone. So you can basically implement this in a naive way, and don't do it that way, but the original initial MPI implementation that were racing to get the confirmant code out there, what they did was they just gathered and broadcasted. You know, it's functionally correct, but it's twice as expensive as you would need. In fact, more than that in practice. And what's an all-to-all? An all-to-all is basically everyone has some message to send to someone else. Right? I'm processor 1, and I have order P messages. Each piece will go to someone else. And the same is true with the second processor. So everyone wants to exchange some data. And they just call this a big shuffle. Some people call this personalized communication, all-to-all. Some people call it all broadcast. There's like different names to it, but I think all-to-all is the most basic name, because other ones, the other way names are sufficiently confusing. And then there's these guys that are particularly useful. The reduction is particularly useful. You have, so now this picture looks like a little misleading. This looks awfully like what happened in gather, except that ABCD on top is not really gathering pieces. It's just there is a function you pass that tells the MPI runtime what to do with ABCD. It can be plus. It might be summing up. So in the end, it might be a single scalar. But it might be a concatenation. You can write your reduction to be a concatenation, which will awfully act like a gather. Then why are you doing that? But you can do whatever, in fact. There are built-in ones, but you can write your own function and register it and call it in reduce. And needless to say, there is a version all reduce, which basically this reduction ABCD appears in every process. There is scan. Scan is this primitive you've probably seen in trick-with trees class. It's also called prefix sum. This is the same thing. So the first process gets the reduction of only the first element, which is itself. The second process gets the reduction of the first two elements. Third process gets reduction to 1, 2, 3, and so on. And you can just nicely write it down. And that turns to be fairly useful primitive for a lot of parallel algorithms. It has some overheads of data copying. Adi, would you mind closing the door? Honest, you know, people can open the door, I guess. Thank you. So one variant, there are variants of these collectives. And one set of variants that are particularly useful are the ones that end with V. Okay, they allow you to, so all the ones we've seen, scatter, gather, the data size is the same. What does that mean? In all-to-all, process 0 sends, if process 0 is sending 2 blocks of data to every other processor, it needs to be sending 2 blocks of data to everyone. It can't be like 2 blocks of data to process 1, but 5 blocks to process 2. It needs to be sending the same size data to everyone. So that's the regular kind. And that allows certain optimizations. But if you want to send, if I want to send 1 piece of data to someone and 2 pieces of data on the second one, I can use this version V, all-to-all V. So of course, the syntax you'll see, and I'm not going to show, now you need to send an extra vector that tells what's the size of the data I'm sending. So it basically tells you the boundaries. Like this piece goes to the first processor. These are the counts array. Okay, and unfortunately, and I should say, there's been some attempts to make MPI 64-bit. Okay, I should be careful. The counts array is currently 32-bit integer. And in this classroom, you probably won't need that, but I have needed in the past, where the number of integers I need to send is more than 2 billion. Okay? It's not that big. Now, 2 billion integers is 8 gigabytes. Now a single node has 128 gigabytes. I can technically send this much data. So I can't do that with standard MPI. There are some extensions you can download, big MPI, whatnot, but that defeats the purpose of MPI. You want something standard, right? So for some reason, MPI still didn't handle that, and you basically need to write a loop around it. You know, you send it 4 times if you need to send 32 gigabytes of integers. It's kind of sad, but that's what it is. By the way, I always thought this V meant variable, but after listening to Bill Grob, which is one of the inventors of MPI, now I know V stands for vector. So everyone sends a different length vector. Not that it's important, but historical purposes. So you know the difference. There are some versions of these reduced scatter. You can read all of these. Technically, the documentation on the web is pretty reliable. So one issue you will see with all these variable length versions, the vector versions, is you have to write a code that's fundamentally duplicated. And it awfully looks like this. I said, so you have to send the counts. You have to pass the counts whenever you're sending data using all to all V, all gather V. Well, the recipient needs to know that he also needs to send this counts vector, right? When he's receiving. Also, he needs to allocate correct size of data, memory to receive that. So usually what it looks like is first, you do an all-to-all before you do all-to-all V, just to be able to send the counts out, okay? And then the recipient basically opens up the correct amount of memory, and then if you're sending some data type that's not an integer or double, or that's one of the standard MPI types, then you have to register the data type, the recipient needs to register the data type, and then you send it, and it's usually you're working with vectors of that are somewhere unpacked. Like you have ordered p-size vectors, and you pack them into a contiguous array, call MPI all-to-all with this code that usually looks like 20 lines. And Patrick was once an intern with me 2 years ago, and here's a nice little library. You can't use this in homework, but perhaps you can use it in your projects, as that's going to do all this magic for you. Basically, he's going to do all the initial data size exchange, register the different types, let's say the pairs in this case, and it will even register the function you're using if it's a reduction. And then, 20 lines of code will be encapsulated for you. So I thought someone needed to do that. I'm glad Patrick did it. All right, now I'm going to illustrate the use of collectives, and also I'm going to illustrate it using subcommunicators. Instead of using MPI word, remember, when I say broadcast, it broadcasts to everyone if I pass the parameter MPI word, but I can form groups of processes myself, and that's usually more efficient. And we're going to illustrate that with a fairly popular algorithm for parallel matrix multiplication. You'll see this in the dense linear algebra class, I believe next week, something like that. You can look at the syllabus. But there is no harm in repeating this, because it's a very fundamental algorithm that's so-called the two-dimensional algorithm, and you'll see what it is. And it's in practice used to multiply matrices whenever you use parallel BLAS. I think it uses whenever you use scalar pack. So here's the fundamental algorithm. So this is a blocked algorithm. At any moment, you're doing a rank k update. Let's say k is the length, the thickness there, and whomever owns that slice, that looks like the red slice, needs to broadcast along its processor row. What does that mean? That means so think of the processes. I have 16 of them at this point, logically organized in a 4x4 grid. This doesn't mean anything about network topology. I'm just numbering processes so I see them indexed in a two-dimensional way. Your network topology can be anything. It doesn't need to be two-dimensional. And then, so this guy is going to be numbered something like P20 if it's zero indexed. Right now, I know I'm P20, but I need to send it to all the processes that are numbered P21, P22, P23. So that's what I mean with along the row. But the same thing is going to happen by this guy, which is P10 and P00. Everyone will send along their rows. And for the B matrix, whomever owns that row slice, there are 4 processes will own that row slice. They will broadcast along their processor column. Okay, so in this example down, but towards the end it will be both directions. And everyone will receive some piece of data, rank K update, and they will do this local matrix multiplication, everyone at the same time, and update their piece of the output. So this is an outer product algorithm. If you think about matrix multiply algorithms, usually we learn in high school inner product algorithms, right? And this is an outer product algorithm because you do a column by the column of A versus a row of B, and that will create an update that's on the order of this whole matrix. So everyone is kept busy because the owner is going to update, and nobody is kind of waiting for other people when they're doing their local update. Nice algorithm. Let's look at what we can do with MPI. But before I tell you the code, I need to tell you one way to create subcommunicators, right? Because I said the people will broadcast along their process row and column. So how do I create those communicators? There are multiple ways to do it. There's a function that is called Cartesian or something like that. But I find split to be much meaningful and more intuitive to understand. So what the split does, you give a communicator to split, and it's going to split your communicators based on this coloring scheme you give. Okay, so there are 2 parameters. One of them is the coloring. The other one is keys. So think of them as you're saying these processors should all be red color. These processors should all be green color. These processors should all be blue color. And then those color assignments will create different groups. And the keys of them will be their new rank within their process. Right? So everyone will call it this way. It kind of looks a little hard, but in example, it makes it much more sense. And we'll get to that. There is a process I included here of what MPI internally does to get this splitter, but you don't need to know about it. You just need to know the semantics. And it's much easier described with an example. All right, so here's the algorithm. I already described this in words. You go over K to 0 to m-1. This one, we kind of do a rank 1 update, but ideally you would do a blocked update because it's more performant. Instead of doing a 1 column and 1 row, you would do a block of them. In fact, the example I'll give you goes to the obscure length, and the block is the whole matrix. And then, these are the steps for all the owner broadcasts along row, owner broadcasts along the column, and the recipient updates. In fact, the way this code looks like, this is pretty simple. So this for loop in parallel means actually it's not executing pj times. All it means is pj different processes are executing this instruction below it simultaneously. So for purposes of parallel running time, this is a single instruction, the broadcast. There's a single broadcast. This is the for all in parallel construct mean. So none of the processes are actually doing the looping. So this is what it looks like in MPI, and this might be wrong. I never tested this because there's no point in writing this code in such a naive way. It's for illustration purposes. So here's the split. First, you you decide your row colors by dividing your own rank by the number of columns. What does that even mean, right? So sorry, the PC, which is the number of processes in your process grid, column-wise. So let's think about what it is going to do. Right, so in this case, there's 4. So when I divide my process ID to 4, I will get This guy will get 0. This guy will get 0. Is that true? Yeah, this guy will get 0. This guy will, and the second row will get 2s. The third row will get 3s. Right? That's what I said. So basically, this will assign a different color to every row, because you know, everyone within a single process row will get the same row color. And then a split function will nicely create a row communicator based on that. And if I, instead of dividing by PC, if I do a modulo PC, then what does that mean? Everyone here will get the same modulo number. Modulo 4 will be the same for everyone in this column, and modulo 4 will be the same 1 for everyone in the other next column, and so on. So now I assigned everyone within the process column a single color. Therefore, the split will nicely split it too. And this rank parameter is just for order. I know the rank will go over 4, but this is only for ordering purposes. I can pass 13, 17, 31, 60 on rank, and what that means is telling MPI that assign them 0, 1, 2, 3. So they don't need to be within the 0 to 4. They just need to be ordered correctly. OK, so that's how I create my communicators. And then I'm going to do the most naive summa with the blocking factor on the size of my whole local matrix. Right? So I basically, if I am the broadcaster at that stage, I mem copy my data to a temporary. Just for coding purposes, you don't need to mem copy anything, in fact. But it avoids me putting an if-else statement within the MPI broadcast. And then I broadcast this. So you can see that everyone is calling the same broadcast, but only the root, which is K, owns the correct copy. Everyone else has junk. But after the broadcast call, everyone will own the correct ATEMP. And they will do their simple local DJAM operation nicely, and update their local matrix, which is MC. I should have used a capital C, sorry. No, this one is wrong. The function, oh, this is all correct. Somehow this is inconsistent. Okay. So the function is inconsistent but correct. So this is all. Of course, this is not going to run if the matrices are not square or not divisible by the process graded row. That's why it's a naive summa. But you can generalize it. It's not that hard. All right. Slightly out of place slide. These are the built-in collective communications. So any questions on this collective and the way summa is run? We'll actually go back and try to improve this a little bit, not in terms of its robustness, but how can we increase the performance? Question?
What does the MPI broadcast know which processor to pick from where to pick the data and broadcast it to everyone?
The root parameter is the one from the last. The one from the last. So the last parameter is the communicator, and the one before that is the root, meaning that that's the guy who has the correct data. And in the previous if-else statement, I basically, if that's whomever is the root at that stage, I copied the correct data to it. So that's how it knows. Any other questions? I am well aware of that size is not defined anywhere. But size is the number of rows times the number of columns in MA and MB. As I said, this is not going to compile. All right, if no more questions, so these are the collective computation operations for reductions mostly, or for scans, just for reference. Here is some exciting piece of lecture that's no longer a tutorial, but some actual algorithms. So how are these collectives are implemented, right? For the purposes of the programmer, it's a single function call, but you have to know the complexity so that you can decide whether you're going to write your algorithm using collectives or some other way. So, and the title intentionally uses the wording, how are collectives implemented in MPI? Because MPI enforces certain semantics. If you have an application that doesn't require these semantics and you think you should be able to write a faster collective, significantly faster, otherwise don't do it. You should be able to rewrite your own already, for example. So what MPI already does, for example, is the first one is kind of trivial. The second one is kind of constraining. If the operation you're defining is not commutative, it should be performed in the canonical order. This looks like the correct definition, but how about floating point? So is floating point addition commutative? I mean, it is kind of commutative, but this canonical order still matters, because if you sum them in a different order, if you sum them in groups of 2 and do a binomial tree, you probably get a different answer. It's just, in the least significant digits, you'll start getting different answers. Neither one of them is correct or wrong. It's just they're different because of the way floating point is implemented. In fact, if you want to try what's going on, is you can get a really large number and a really small number. A bunch of really small numbers. Let's say you have 100 0.001s and 1 million different answers. So now sum them by starting from the smallest to the largest. First sum the 0.001s, and then at the end add the 1 million. And then in the other extreme, start from the largest to the smallest, and then you'll get a different answer, especially when you sum a really large number with a really small number. The rounding errors are pretty interesting. And this is not the class to talk about it, but know that it might have some limitations there. Anyway. And finally, this is what it's talking about. The third aspect, the language there is not non-mathematical, but all it's talking about is associativity that I described. So it says you should be striving for it, but not strictly required, which is kind of a weird way of describing a specification. What does that even mean? Like not required, but strive for. So these are the kind of collectives that are commonly used in MPI. I didn't include the vector size versions because it usually depends on the length of the vector, and the formula gets even more complicated. These are the lower bounds, like what is the best you can do in the ideal case. And you will see that the latency in all of them, the number of steps the algorithms needs to take, is usually logarithmic on the number of participating processes. P is the number of processes. And why is that the case? Because at any point, you can basically send a message to 2 people. That will send a message to 4 people. The base of the logarithm can change, particularly, but the reality is these numbers will not change. And you can basically say, what if I just broadcast it to everyone, like sending a single message? That's not going to work very well either, because then your local latency is P. Yeah?
Yeah, so is that actually assuming the structure of the node is like a dragonfly or?
No, there is no structure here and the latency. So basically what's happening here is you can basically say, instead of sending 2 messages at once, I will just send 4 messages, and then everyone will send it to 4 neighbors. You're kind of benefiting from the base of the logarithm, but then you'll get a constant that's, instead of 2, you'll get a constant 4. So you're going to lose there. So therefore, I believe these are lower bounds actually hold. This is like the old school. Before the internet messaging came out, when your parents tried to communicate some information for everyone in the classroom, what they did was this, telephone trees. Do you remember that thing? One person calls 2 people, and everyone calls 2 people, and eventually in logarithmic steps, everyone knows the news. The bandwidth terms are pretty basic as well. I'm not talking about algorithms here, just thinking. So what does broadcast mean? So by definition was some root had order and data it needed to send to everyone. Well, of course, the best you can do is that much data needs to leave the root, which is order and times the inverse bandwidth. There's a little bit of reduction on that for some operations. For example, gather. In gather, everyone already had 1 piece of data, and they're trying to get P-1 pieces of data from everyone else. So the ratio is just a little bit less. the amount of data that needs to be received, because everyone already has some data. In broadcast, P-1 processes doesn't have any data, so there's just a little more data exchange that needs to happen in broadcast in the best case, and the computation only makes sense for the cases when there is a function, like a reduction function. Because if there's no function, then there's no local computation that needs to happen. And for the node, you can read the text. So I put the reference. There is some assumptions here in these lower bounds. OK, all-getter algorithm. I choose this algorithm to describe because the other ones look awfully similar. And I'll describe what it means. So the simplest algorithm you can think of is assume all the processes are in a ring. Again, this doesn't need to be, they don't need to be topologically, physically on a ring. I'm just assuming that I'm numbering them in such a way it's P0 to all the way to P5, and I'm just going to be doing nearest neighbor communication. So P0 will communicate with P1 and P-1. So it's a torus. So at time t, everyone sends it to a right and receives Neve data from their left. Okay, so what do they send? Okay, they initially, for the time 0, they send their original data. At any time after 0, they just forward the data they received in the previous round. So you just basically let the data go merry-go-round for P-1 stages. And what's the complexity? The bandwidth hits the lower bound, right? Because everyone is receiving the minimum amount of data they will receive, which is P-1 divided by P times n. But the latency is higher than logarithmic because there is P-1 steps. This is significantly higher latency than you would like to achieve. So therefore, there are other algorithms, of course, which is this recursive doubling. Every computer scientist probably could have figured this out by themselves. So what's happening at any stage, at stage t, processes that are apart by 2 to the t exchange data. And I specifically say exchange. So basically, they send and receive from each other. So in the second stage, now they're 2 to the t is 2, so 2 to the 1 is 2. Then 2 hop neighbors exchange data. And I might have an indexing problem here, but that's OK. It all depends on what you mean with how you start t. I think this is correct because I assume original t is 0. And then 4 hop neighbors exchange data. And finally, if you count the total number of data exchanged, basically the data you're exchanging is not the data you just received. It's the total amount of data you have so far. Like at first stage, you only send data n over p, which is your local initial data. At second stage, you send 2 n over p. At the third stage, you send 4 n over p, all the way to 2 to the log p minus 1 over p. And if you sum this thing up in the binary t leaves, you'll get 2 to the log p divided by p to the log p is p. So this is all going to be exactly like this. And then there's an n here. Damn, yeah. There's an n forgotten there, and it will be fixed before the slides are up. Slides might be already up. So what's the number of steps? Logarithmic, because of the way recursive doubling works. And it looks perfect, except that the example only shows the number of processes when in the case where the number of processes is a power of 2. When the case is not a power of 2, this algorithm is tricky to generalize. So what people usually do, instead of dealing with the generalization, they just assume that there is a ceiling of, double the number of processes. If you have 17, you assume that there's 32, okay? And then you kind of simulate it with empty data. So you lose some, you basically get an extra factor 2 all over the place. So someone noticed that this algorithm can be slightly modified. Actually, it's not even the devil is in the details. This algorithm, the way I'll describe, will look awfully similar to recursive doubling, and you'll say, isn't this the same algorithm? So now look at the simulation. What's going on? At step 1, step 0, from the initial data, everyone received data from their right neighbor, okay? This is different than recursive doubling, because in recursive doubling, everyone is exchanging data. So basically what was happening there is P0 was sending data to P1, P1 was sending data to P0. Here, it's always push the data to your right. But you push it to your right neighbor by one hop. In the second one, you get, you push data to your left. And that's an important aspect, because if you push your data to your right, the ordering will be incorrect. There'll need to be a permutation at the end. This one actually nicely puts the data in the correct order. And in the next step, you basically receive data from your 2-hop neighbors, and the next step, you'll receive data from your 4-hop neighbors. What does this look like? This is actually the butterfly network's pattern, right? You first get data from your 1-hop neighbors all the way from your left, and then the 2nd-hop neighbors all the way from your 2 distance. So this is often like butterfly. And another difference is you don't actually need to assume that the number of processes is doubled. You can generalize this to non-power of 2. In fact, this is a 6-process case, so it's already non-power of 2. After floor log P steps, now you're done with your regular steps. Instead of receiving data of length 4, you only need data of 2 blocks in the next step. So you receive irregular size stuff, which is only order of 2 in this example, but formally it's this much data that you need to receive in the last step. Now all your communication is over after this point where you did sealing of log P steps. Remember, sealing of log P is actually different than 2 log P. This is a little better. And finally, you need to do a local shift. It's not a permutation. You just need to change the pointers of the beginning and your end of your queue so that the final all-getter is in the correct place. So this looks like a better algorithm for non-power of 2. Does the experimental data support that claim? And it actually does. So just look at the left. This is old data, but I believe it's still correct. The Brock algorithm that we just described has this curve that's this dashed line. And the recursive doubling has the flat line. So you see that recursive doubling, sometimes the lower is better. The y-axis is time. Recursive doubling can be just as good as Brock and even sometimes barely better, but only when it's power of 2. Every time else, Brock algorithm is faster. So it's like a nicer, smoother curve, so you don't need to worry about whether you have a power of 2 or not. What is more surprising is the right figure, which is showing that the ring algorithm, okay, sorry, this is for small messages, 16 bytes per message. What's showing on the right is for really long messages, message length order of megabytes as opposed to kilobytes. So what do we see? For 1 megabyte data, everybody is the same. Ring algorithm and recursive doubling is the same at least. But then ring algorithm is getting faster and faster. So this is kind of surprising, right? We had a really big latency. But why is this beating the recursive doubling, which has better asymptotic time? Any idea?
Just still because of overhead?
Yeah. But why do you think there is more overhead?
Because maybe the data set size is still too small.
Data size is big. Actually, the bigger it is, the better. So remember, these algorithms have the same bandwidth costs. One of them has a higher latency cost. Yes?
Is it because creating recursive calls is expensive?
It might be, but recursive doubling doesn't need to be implemented recursively. You can unroll that. The actual reason is nearest neighbor communication is usually still faster than sending data to your hop 4, hop 8, hop 16 neighbors. So remember, ring algorithm is only doing nearest neighbors, and the part that it loses is the latency. But when your message sizes are 8 megabytes, the latency is no longer the dominant factor. So that's basically the difference. So therefore, what MPI does is actually a big poly algorithm. When the message sizes are long, they use ring. When the message sizes are medium and the power of 2, they use recursive doubling. When the message sizes are small or messages are non-power of 2, they use Brock algorithm. And then what they mean with long, small, medium changes from architecture to architecture, and the implementation will define those things for you. And unless you know what you're doing, probably not worth changing it. And some of the time that's spent before a computer is accepted formally at a supercomputing center is this months of work of optimizing those parameters. Because that machine will usually be in service for 3 years. It's worth optimizing for. It's going to save a lot of electricity. And the top line in the slide shows that the reason I showed altogether and not other collectives are they're awfully similar ideas. So, for example, in the reduced scatter case, instead of the all recursive doubling, you'll be doing something called recursive halving. Same idea with the data being halved as opposed to doubled. Or the all reduced algorithms, instead of concatenating data, as in the all-gather case, they will actually internally reduce the data before they move the next stage, because that's the definition of all reduce. So there's not much difference in the other algorithms, but you can read this paper. It's fascinating for other algorithms. All right. Any questions so far? Okay. I think I'm pretty slow today. Let's see what we can do. I think I have a reasonable idea of what's important, what's not to cover. There is a concept called barrier. All I need to say in the slide is you probably don't need to use it. Almost all collectives are synchronizing by default, so you can reasonably think that there's an implicit barrier inserted there. So people use barriers for timing or debugging. If you're uncertain about the correctness of algorithm, and you just need to insert lots of barriers to make sure things are correct, you're probably doing the wrong thing. So you should go back and say, what am I doing wrong? In a study that one of my colleagues have done, they looked at the really long 4 million lines of code in NW-Chem, it's a chemistry application, and they basically did a static analysis of the code and figured out that at least half of the barriers can be removed from the software and wouldn't change correctness, and it would make the code run 15% faster. So don't just blindly insert barriers. Okay, so buffering. We talked a lot about sending data, receiving data. We didn't tell what's happening under the covers. And this is a nice tie-in to non-blocking operations. So all the examples we gave, both for pi computation and for summa, are blocking operations. So what does that blocking mean? Usually what that means is your send or receive or broadcast doesn't complete until your outgoing buffer is your outgoing buffer is empty and your incoming buffer is full. Okay, so you can implement this 2 different ways. One of them is you can basically move your user data to your local buffer and then continue your program. And then the MPI will move that data from that local buffer into the network somehow under the covers while your program is still continuing. Or you can basically wait until the data directly from your user space has finished moving along the network. So you can see there is a trade-off here. In this case, you don't need to make a copy. So there's a memory benefit. But you have to wait until the thing is completely communicated. In the previous one, you have to make a local copy. And you can control these things. So basically, the ones that we have seen, the send is this version, standard blocking send. But you can do a buffered one, and we'll get to that. So what's the problem with the standard blocking send? Let's say I wrote this code, and this can deadlock. Why? Because the process 0 is trying to send, and processor 1 is trying to send to processor 0. Okay. And then what if they don't, neither one of them progress? Because there is no matching receive yet. it's actually remarkable that this is not always deadlock. If there is a MPI implementation does a buffering in the end and sends it to the local buffer and lets you continue, it might not deadlock. But this is kind of the dangerous part where you try to debug cases where it sometimes will deadlock, sometimes it won't. So corrections to this, order them correctly so that the sends and receives are matched. This is the most trivial way to do it. I usually like send receive for these pairwise exchanges. Basically, MPI does this thing for you. Send receive is a primitive that does both exchange between two pairs of processes. And you don't need to worry about which ones are sending, which ones are receiving. And there are other ways. You can do buffered send. You basically force MPI to use this logic that is pictured here. You tell them, the MPI, that here's a local buffer you can use, and you should be using this. So then it will return. The send will return immediately and will use your buffer. Now you have to specify a buffer. That's kind of your problem. And there is syntax to this. This is not that just putting a b send. You have to create a buffer. You have to call a function that looks like MPI underscore buffer underscore attach, which basically telling MPI use this one. And then after that, you have to detach the buffer, making sure that you only do it after the progress, the message has been received by the other side. And then you have to also delete the buffer. So there's a little bit of bookkeeping for this purpose. So that's why you probably won't see a lot of uses for bsend. But you'll see a lot of uses for isend iReceive, which is really convenient. All you're saying is I doesn't mean, what do you think I means, actually? So let me tell you what it does. isend asynchronously, so isend tells MPI that I want to send a message to process one, but it shouldn't block. Okay? It just needs to continue, and there is no guarantee that the message will be sent at any time until you call a function that looks like wait all, wait, there's variants of this test. And then isend is the same as it basically asynchronously executes. So I here means immediate. And it just means not immediate send, it means immediately return after you. So all MPI does is checks the parameters and then returns and it also returns your handle so that you can later test whether that message has been sent, completed, or not. And then you can pass those handles to tests or waits. So this kind of fixes the ordering issue. You can do it everyone can send first and receive later, but they will somehow be matched under the covers because the whole synchronization is happening in wait all. The problem with this is whether there's actually any progress before you call wait all depends on the quality of your MPI implementation. Some MPI implementations, as soon as you call isend, it will start a progress thread. Like that thread will ensure progress of the message. Some MPI implementations will just do nothing until you call wait all. And that is awfully the choice of whether you have free threads, whether your network supports remote memory operations, because MPI implementations doesn't like to disturb your main computation. And that's one of the issues with MPI. But I think this is a common issue that has a lot of asynchronous messages doesn't guarantee any progress. All right, so this is the I, immediate. I send, I receive, this is the syntax, if you care. And the last one is the handle that I mentioned, which is the request. They didn't call it MPI underscore handle, they call it MPI underscore request because handle was used for something else.
In the previous slide,
yeah.
What's the difference between the two calls except for that you have to explicitly allocate buffer?
What is the difference between two calls?
Yeah, it's semantically.
Semantically, there is no, yeah, you have to give your own buffer. Basically, in isend, iReceive, there might not be any buffering underneath the covers either. So you cannot, so when you say blocking send and you give a buffer, it already is copied to the buffer after the function returns. So you can reuse that user space data. You just shouldn't touch the buffer you attached. Remember, you gave them an empty buffer to use, and you also gave the data that you're sending. After bsend returns, you can reuse that user space variable because that'll be copied to the buffer when you call it. In iSend, iReceive, there is no buffer, and there might not be. So you cannot touch the memory location until the wait alls are all returns. So there's potentially garbage there until you synchronize. iSend, iReceives are much more popular. So in fact, here's a hint. Before I started giving these lectures, I didn't even know bsends, breceives. Is this recorded? Okay, so these are different versions of waits. You can wait for everything that's out there. You can wait for any. What is that? What's the difference? Well, basically, wait all means you have to, every one of these handles needs to finish. Wait any, if one of them finishes, it's okay. Wait some is, God knows why they created this. Like, why can't you just use wait all to handle this case too? Because you basically tell it which ones you should wait. And that's just, you can just call wait all with that subset. Regardless. More versions. So there's ready mode that you can read about, which just basically says, whenever you call a ready mode send, there's already a receive posted by the receiver. So probably hard to ensure, but it's nice to read these things and know about them. But I want to talk more about the collectives that are non-blocking. So here's one that I'm going to use in an example. This is iBroadcast. So this is awfully like broadcast, except that it immediately returns. So why would that you use this? And it's going to be on the next slide. But the differences between this versus the iSend, iReceives is, one of them is this last bullet that I highlighted, no matching with blocking collectives. What does that mean? If I do an iSend, let's forget about this example. There's an iSend here, and there's just a receive there. That's actually valid. It will match, and the receive will receive anything. Receive will receive iSend, receive will receive bsends. Anything that has a send on it, receive will match. Because they're a different function call. One of them is sending, one of them is receiving. Broadcast, on the other hand, needs to be called at the same time by everyone. So there's not going to be a matching. A broadcast on a different process will not match an iBroadcast in some other process. So that's a little bit of a difference. Similar restrictions, you should not be touching the buffers during the execution until you call a wait and make sure that it's finished. Once again, there is no guaranteed progress. These are the same as iSend and iReceives. So there's an I version for every collective as far as I know. These happened after MPI 3. So until MPI 3, there were only immediate sends and receives, but no collectives. Now there are collectives. And why would anyone need this? Let's say one process is slow. You call MPI broadcast. Remember, this is blocking. Everyone needs to wait. So that will delay the whole execution. And in the extreme case, when there's system noise, operating systems sometimes wake up processes, but they will only wake up one process. Now everyone else will need to wait for that guy. So the immediate returns will fix this problem. Even if one guy is slow or two guys are slow, you're just going to return, and they will catch up later. So it's a much noise-resilient way. And it allows for overlapping and communication and computation, and that's the example we'll go over. So how is this going to happen? Remember Suma from, I don't know, 20 slides ago? The same thing, there's nothing new here. How can I implement this code with, so why would I even want to implement something new? So here's what the issue is. There is a receive call for its own block, the block of A that I'm going to receive, and a receive call of the block of B. It is quite possible that these pieces will take just as long as doing the local matrix multiply. Right? So if this takes 5 seconds to receive the data, 5 seconds to do the local matrix multiply, I'm taking 10 seconds. well, what if I started sending data for the next thing that I'm going to read while I'm computing this one? So basically, I'm going to post and broadcast for the k plus first piece of the data while I'm computing the dgem on the kth piece. Right? It's going to synchronously continue, hopefully, if there's implementation is high quality enough to ensure progress. And then by the time I need to do my next dgem, it will be already there. So that's the best case. Basically, you can overlap the same amount of computation with communication. You can take your time, divide your time by half, if these things are balanced. If things are not balanced, you can gain more than 2x for the noise resiliency reason I talked to you about. Like if one process is taking 10 seconds, the other one is taking 1 second, and at the other stage, the things are reversed, the noise resiliency case is a stronger case than overlapping, because the maximum you can benefit from overlapping is 2x when things are balanced. When things are not balanced, the things you can benefit from immediate functions is significantly more. So here's what it looked like. Okay, so first, of course, I need to do something, and these functions are highlighted in red are the differences from the previous version. First, I need to basically, remember, I was sending all of my data in the broadcast case in this naive summa. Now I need to I want to send only half of it, so that I can send the second half while the first half is computing. So I'm just going to call a split. I'm going to split my local matrices into MAA and MA2. So first I'm going to send MA1, and then I also will start sending MA2. And then I'll wait on MA1. As soon as it's done, I'm going to start computing on MA1s, the recipients, while MA2 is still continuing. And then I'm going to issue MA1 of the next block and so on. So this kind of looks like the code will double the size, because I do a broadcast request, and I do a wait call, do my matrix multiply, and then I do another iBroadcast request, wait all. But the thing you have to remember is, unless I did it wrong, I issue broadcast here, but I'm waiting for the previous broadcast, not this one. So if this was waiting for the broadcast immediately above, there was no point, right? So it's easier to see in this version, because this guy's iBroadcast is off the slide now. In the bottom iBroadcasts here, the wait all immediately succeeding that is not waiting for these guys. They're waiting for the broadcast at the top. Remember, so I return from iBroadcast. So that's the nice thing. You can, in ideal case, you can overlap all of these things. Whether you're going to achieve that depends on the quality of the implementation. So I repeated that way too many times, I think. Questions? OK. Well, there's bookkeeping for the outside the loop case. Maybe I went overboard with this example. All right, so in the last 20 minutes, I'm going to go talking about threading. This is actually conceptually easy. It's not going to be a lot of thinking, but so I think we can go faster. And I'm probably not going to talk about one-sided operations for one simple reason. The whole UPC++ lecture will talk about one-sided operations. But all I want to say about MPI one-sided is it also exists in MPI, much more painful. In fact, MPI has 4 different concepts of one-sided synchronization, and very few people kind of understand which one they should use at any time. And MPI doesn't like to break backwards compatibility, so they're not going to delete some of the versions. They just keep adding. It's like inflation. Here's threading. I already said in today's technology, you do need to use some amount of threading, even if it's not for performance reasons, but for memory consumption reasons. But there's usually a performance reason due to network interface card being overwhelmed with MPI calls done all at the same time. So threads on MPI, OpenMP, and pthreads are common modes. Probably you should use OpenMP for the reasons I talked earlier. So there are different ways of doing this hybrid programming. MPI plus OpenMP is the most popular. Some people do all MPI, and they call this MPI plus MPI. What does that even mean? It means basically you create groups of MPI. Your groups, local groups will handle anything within the node, and only one MPI leader will send it to other nodes. That's kind of possible too. It might actually make life easier for programming purposes, but I'm yet to see a convincing paper with the performance results that's actually more saying that this is more beneficial. This is what the model looks like. But more important thing, you cannot start, you cannot do MPI calls from multiple threads without first calling something called MPI init underscore thread, which is the bottom of this slide. If you're using multi-threading and only calling MPI underscore init, you're doing something wrong. It might run, but it's an erroneous program. You have to start your initializer with the thread call, and you should basically say what you're requesting. There are 4 modes. Single means, well, there's no point in requesting single, because that means there's no threading allowed. Okay? Funneled means you're requesting permission to use threading, but only the master will ever call MPI. That's usually supported too, by the way. In reality, even if the MPI implementation doesn't accept it, they probably still are supporting it. Serialize is a little trickier, and I will show examples you'll understand. Again, here, only one thread will ever do MPI communication at any time, but that might be a different thread. At first iteration, it might be thread 1 that's doing communication. At the second iteration, it might be thread 2. But there won't be simultaneous MPI calls from different threads. And MPI thread multiple is anything goes. Like anyone can do any MPI calls simultaneously at the same time. That's the highest level. There's some restrictions, but these are in increasing order of strictness. So let's say you request MPI threaded multiple, and the implementation returned, as in the provided variable, MPI thread serialized. So basically, it tells you that don't call MPI from different threads at the same time. I don't support it. And it also tells you that not only serialized is OK, funneled single whatnot is of course OK. It's just inclusive. But definition already includes it. That's all. And why doesn't everyone support MPI multiple? It's tricky to get right. It's more expensive to get right because you have to make sure that memory regions are properly locked. There are some MPI internal counters and variables that needs to be protected if you do higher levels of thread support. But things are getting better. When I did my PhD, almost nobody supported MPI multiple. I think everything that Cray installs and you'll have access to will support MPI multiple today. It's good days. So this is what MPI thread does. There's no threading. Trivial MPI program. I didn't even call MPI in a thread, of course. For funneled, remember, only the master thread can do it. So now I need to call MPI in a thread. I need to request MPI thread funneled at least. But I do my MPI calls outside the threaded region. Right? So there's some threading, but only the master is doing it. Fine. Now, here's the difference between serialized. Now my MPI calls are within OpenMP parallel regions, except that is protected by a critical. And remember what critical did? Critical tells that only one OpenMP thread can execute that line at any time. It doesn't mean that only one thread will execute it ever. It means 2 threads will not execute it at the same time. So that's correct as well. And finally, anything goes. So basically, you put your MPI stuff within your parallel region, multi-threaded region. Everyone will do MPI stuff simultaneously. And this is correct as long as your semantics are correct. I'm not saying that you can't write wrong code. This is just MPI-wise accepted. The reality. everything I said is already included in these slides, or vice versa. So the hard thing I want to spend some time is MPI thread multiple. So what are the semantics? One of them is pretty much like OpenMP semantics. When multiple threads make MPI calls simultaneously, the outcome is if they execute it sequentially in some order. Okay? It's not, that kind of makes sense, right? So the operations are indivisible. You can think of it that way. If you can sequentially, you have to be able to think about different orders, but it's not going to be that in the middle of your MPI call, that thread will yield, and suddenly a different MPI call will start. They're serialized in some order, but you can't reason about which order they're going to serialize. It's just they'll be indivisible. And blocking means that if you make an MPI blocking call in thread 0, that doesn't block anyone else. Thread 1, thread 2 can continue doing whatever they're doing. That's fine. So here's the correct example. So this might look, so thread 1 in process 0 is trying to receive a message from process 1. And thread 2 is trying to send a message to process 1. So this is not incorrect because I don't know the ordering of threads on process 1 and 0, but what my blocking rules say that even if thread 1 in process 1 is blocking on the receive, that won't affect what thread 2 in the same process will be doing. So it will not block the other thread, which means it can successfully send, and that will be matched by the receive on the thread 1 process 0. And similar reasoning goes the other way around. So this will not deadlock, simply because one blocking call in thread 1 doesn't block the sends in the thread 2s. So that's going to be fine. And just because of the blocking rules. Okay. Incorrect example, and this is kind of intricate. I didn't know about this until now. It turns out broadcasts can match barriers. And it might happen. So this will try to, sometimes, depending on the order, because there's no guarantee that thread 1s will execute before thread 2s, it might be the case that the broadcast matches with barrier, and then things will crash. Why is this even allowed? I don't know. But this is a more realistic case, where one thread is trying to do broadcast, and you're stupid enough to put your freeze on the other thread. Of course, before your broadcast be over, you might actually free the communicators, and that's a problem. So that's not correct either. Here's the current situation. Again, I talked to you about these. All MPI implementations, of course, support single. Almost all of them support funneled, even if they don't admit it. Many of them support multiple. In general, funneled will be good enough for a lot of applications, unless there is some asynchronous operations going on, there is some load imbalancing happening, some dynamic execution. You won't probably need thread multiple. However, the time that you need thread multiple is what is it? Remember Amdahl's law? Right? You do remember Amdahl's law. Basically, the portion of the program that you haven't parallelized will eventually come back to haunt you. That's the layman's terms of Amdahl's law. When you're calling MPI funneled, which means that only the master process is communicating, you're creating an Amdahl's law bottleneck on that MPI function call. So using MPI thread multiple will eliminate that issue because you'll be making simultaneous communication calls. So, you know, here's how Amdahl's law plays with communication. And to my good surprise, I actually have a little bit of time for one-sided communication. But any questions before that? Yeah.
So what are the performance implications of using multi-threaded MPI versus doing a hierarchical OpenMP reduction followed by an MPI reduction from the master thread?
So let me repeat this question. So one option is, let's say, you want to use an example of reduction? Okay, so in one case, you do an OpenMP reduction locally, and then you call an MPI reduce in a funneled way, in some sense, versus?
No, just in the sequential section of the code.
Yeah, okay. And in the alternative was MPI thread multiple, and everyone would call reduction. Very good question, and I don't think I know the answer to it. So in theory, it sounds like MPI thread multiple will be faster because you would actually take advantage of every process, every core that's available to you. But remember, there are two downsides with MPI multiple. One is there's more data that might be sent, and it's not exactly true. So the reason this is a hard question to answer is if the MPI implementation is naive, then everyone will try to send data, and the reduction will happen. Essentially, you will be sending T times more data around. But if the MPI implementation is smart, it might do the reduction locally first, figuring out that you have 16 MPI processes, 16 threads at the same node, and then only send one piece of data. So it's not really clear what implementation does there, and it's actually a pretty good use case to benchmark, if anyone is nerdy enough to do that. It definitely eliminates the Amdahl's law bottleneck in some sense, but it also has the added effect that MPI, whenever you get MPI thread multiple, you have a performance penalty. You're linking to a slightly less optimized MPI implementation because it needs to protect memory regions. It's actually a very good question, and just to repeat, a good test to run would be to do a reduction with MPI thread multiple. Every thread calls a reduction. In fact, you don't even need to do threading. You can probably do a reduction by everyone, and you map MPI processes to cores. That would be one way. And the other way is you do OpenMP reductions, and only the master thread calls MPI reduce. And it's going to be interesting to see what the performance is. Is the new students for this class or for the next class? Okay, good. I'm just curious whether it's possible to come in the last minute. It is always. Hey. Anyone is welcome anytime. One-sided operation.
Hi.
Yes.
Just to be clear, for homework 2, we have to implement the part 2 using purely MPI, right?
Yeah, you don't need to do hybrid programming, if that's the question.
Just clarifying.
But for projects, this probably is a very good avenue. Most high-performance codes on large distributed memory machines are hybrid today. And that was not the case 10 years ago. So that's a big difference. So I'm going to skip these illustrations because I want to get to this one. So what's happening when I do a two-sided communication? So look at the picture. There's a processor. There are two processors, and they will be sending data to each other with two-sided standard MPI. Here's what happens. To the recipient basically creates memory space, and the sender creates memory for the data that it will send. MPI implementation takes that data and then ships it over the network. And then the recipient puts what the data is going to receive to that area, and it gets filled. And it again gets copied back. Simply, that's basically what happens. The main point is there are two processors that are involved. When you do one-sided, the sender sends the data. The same thing happens, except the processor on the other end does not need to be bothered with this. Basically, the MPI implementation, if it supports direct memory access, will directly put that data into the memory space of the recipient without bothering the receiving processor. He doesn't need to post the receive with a buffer intentionally. So what's the benefit will be like you do send and receive. If process 1 has some delay, then everyone will wait. The sender will wait for that delay to pass so that the receiver will post. In the one-sided case, even if process 1 is busy, process 0 can put data into the memory space of process 1 because it doesn't need to involve the processor. That processor can be stalled for whatever reason. That's not important. Okay? So that's the general scheme. So this is some places called MPI RMA, remote memory access. So there are some places there's one-sided operations, some places call it RMA, and this distinction happened going from MPI 2 to MPI 3, and you shouldn't probably worry too much about it. So I'm going to talk about how to make this memory accessible. One of them is, I say put data, but I can't really put data to a different processor's memory unless that process first made it available to me, because I don't even know its address space looks like. I can't just randomly assume that the address in my local stuff also corresponds to the same address in the other processors. It might be a different virtual address, right? So what happens is whenever you call malloc or new, all that data is local. If you want to make your local memory accessible to other processors, you have to attach so-called a window to it. So that's basically, that window is an MPI terminology for the memory segment that you made available to other processes. And what usually happens is once you declare a memory region as a window, the system will register it on the network, will make everyone else know that, okay, these addresses are available to you to write, and these are the physical addresses. You can basically directly write to that physical address. So there's some sort of broadcasting happening under the covers when you call window create. Okay. There are many ways of doing this. Some of them are a little too complicated. Some of them are only making sense when multiple processes share a buffer and so on. I'll just talk about the most common useful ones. So window allocate is, it creates a window with some certain size and makes it immediately available. Here's the example. MPI win allocate, here's the size and where it needs to be allocated. The address is given. The int star A is the address. So basically, MPI is allocating memory for you of the length you want. So this is the one I like, because the other one is you create the memory and then you basically upgrade your memory space to somewhere else. This one is faster because MPI actually can allocate the memory in a region that's faster and easier to access to other processes. And then you have to delete this space. In the alternative, you create dynamic is this other one that I talked to you about. You create a window that's initially empty, and then you later attach data to it. So here's the example. You create a dynamic window, and just initially empty. You create private memory using malloc, and then later you say, I want to attach my private memory to this window. Now MPI will need to do magic. It needs to know that your memory is not exactly where it wants to be. It needs to do additional bookkeeping, some other translation potentially from the memory space to your local space, but it will do it for you at slight expense. This is more convenient for some people for programming purposes. But know that this is probably a little bit less performant than letting MPI manage the memory. And here you have to deal with the memory. So there is a call free A, right? This is important. There is free A here. In the previous example, there is no free A because MPI allocated the memory. If MPI allocates the memory, MPI will free it for you when you call win free. If you allocated the memory, MPI will not free the memory you attach to it. You have to free it. You still need to call detach and window free. But for the memory free, you have to do it yourself if you create it yourself. It's actually very easy to remember. Do it yourself, clean it yourself. It's like pack out. And data movements, once you create a window, you can put memory there. Everyone can put memory there. And get. Once a window has been created, any processor and process can receive directly from that memory, issuing a get call. These are the two fundamental ones. There are other ones, accumulate, compare and swap atomic these are, and fetch and op. These last two ones are atomic, and you can read about them later. We don't have time for it. And you will see a lot of similar concepts that are coming up in the UPC++ lectures. Not worth spending too much time here. Of course, the final thing I want to say is you issue the get. How do I know that the get completed? That's the problem, right? Or it's actually worse in the put. I say put. I mean, the put will immediately return to me. But how do I know that that data is there? And in fact, how does the recipient know that that data finished? So there's a concept called synchronization, right? And there's, unfortunately, I think, at least 3 and apparently 4 different ways of synchronizing. And half of them start with active target. For me, personally, it doesn't make sense to have the target active if your goal is to get one-sided operation and not disturbing the other processor. So even though there are good use cases of active target, for the applications you really need one-sided operation, you want the passive target synchronization. That kind of makes much more sense, right? And the standard passive target synchronization is this lock and unlock. So you basically issue a get operation. Whenever you do unlock, you know that the get completed. It's unfortunately called lock and unlock, but the naming should be start epoch and epoch. It's probably better, but they use the epoch words for active target case, so they had to use a different word for the passive target case. So here's the complication. But this is the syntax, and it will basically, you make an MPI called put get within the locked windows, and no concurrent accesses to same process are allowed. You can say, if you put exclusive, no other process can access that locked region. At the same time, if you put shared, you can. So just know about those. And that's pretty much the end of it. What I didn't cover in MPI is I didn't cover all these Cartesian topologies. I didn't cover task creation and dynamic destruction. Almost no good implementation exists for that concept, unfortunately. I/O actually exists. Good MPI I/O exists, and it's much faster than writing individual files. So if you ever find yourself dumping a different file per process, look after MPI I/O and try to eliminate that, because it's much slower to create thousands of files at the file system than to create one shared file, usually written by a collective operation, MPI I/O. There are lots of presentations about MPI I/O, so Google is your friend. Questions? OK. That means get out. I think it's mostly for me, but do these doors lock? I guess.
I think so.
Oh, that's why they keep it open. All right.